Is an ARC Future Fellow and Senior Lecturer at the University of Technology Sydney, so here, is currently leading a research group in the Centre for Technology in Water and Wastewater. Now I think I'll stop there because I'm sure your presentation is going to do wonderful justice better than my introduction, so please join me to welcome Dr. Fu to give his talk on cost-effective water production as our keynote speaker. Thank you very much.
Thanks, Michael, for the introduction. Good morning, everyone. I'm Fu. Yeah. Today, I'm more happy to share our recent research in the development of new technology for cost-effective water production. So first, what I do, as you can see, my research mainly covers three research fields. So namely, development of the radical polymerization technology, the development of new membrane materials for CO2 capture, as well for energy generation. And today, I will talk this topic, the development of functional hydrogen materials for the solar vapor generation strategy. Okay, so first I will talk about the research motivation, sorry. So that is the water scarcity. So this term refers to a situation that under the situation where the water supply or water quality cannot meet all or cannot fully meet all the by all the users and under the current arrangement. So indeed, yeah. So currently, about 7 million people, 700 million people in 43 countries, so suffer from water scarcity, and it is predicted that by 2025 this number will increase to 1.8 million. Yeah. And by that time, 2/3 of the world population could live under this water stress conditions. So this situation highlights the development of water production technology. Yeah, but we know that since last century, since 1960s, our membrane technology has become mature. Yeah, can produce a lot of desalinated water. However, the desalination plant requires huge investment, initial investment, and the operation will also costly and consume a lot of energy. So in addition to this, the disposal of a large amount of this kind of green water will also cause environmental problem. So therefore, researchers propose this technology, namely the direct solar vapor generation. This can be considered as a cost-effective alternative for water production. So briefly, as shown in this figure, you can see, so the researchers developed functional hydrogen materials and placed them on the surface of water. And the hydrogen materials generally consist two kinds of components. One is the photothermal materials, the other is the hydrogen matrix. Oops, sorry. And then we place these hydrogens on the surface of water in a closed system under sunlight irradiation. The photothermal materials can efficiently convert solar irradiation to heat, facilitate vapor generation. And the generated vapor in this closed system will be efficiently condensed, and the distilled water can be collected for use for drink, for example. So therefore, heat management strategy, including developing new photothermal materials to improve the photothermal performance, and reduce the heat loss, as well as the water management strategy. For example, develop advanced hydrogen matrix to facilitate water transport, has been developed and has been considered as efficient strategy to improve the SVG performance. In addition, so we also need these hydrogens can effectively reject salt, and if the hydrogen can also have some antimicrobial properties, will be fantastic, because this is good for the practical application. So accordingly, our research group focus on the development of heat management strategy. So we synthesize a series of photothermal materials, including 1D nanoroots, 2D nanosheets, or 3D nanoparticles. And we compare their performance in the terms of the geometry. So in this study, we investigate the influence of the geometry of these materials on the photothermal performance. So this study, the initial study was conducted by my student Casey. So by varying the mole ratio of the initial materials, so through the same hydrothermal process, we first successfully synthesized this metal oxide or semiconductor photothermal materials. One is the 3D magnesium oxide particle, the other is 1D conventional magnesium oxide and nanorods. Yeah, as you can see, under 10 minutes of solar irradiation, both of these materials can show very high photothermal performance. Yeah, so for the 1D photothermal materials, they can achieve 84 centigrade in 10 minutes. And then we incorporate this photothermal materials into the polymer hydrogels. This is a PVA polyvinyl alcohol solution, 10% mass loading, and introduce 1% of this photothermal materials. And I did cross-linker. Yeah, after cross-linking and frozen thaw, so we can successfully prepare 2 kinds of hydrogels containing different photothermal materials. And then we characterize the map or ICM. Through the ICM image, we find that the 3D nanoparticle or 1D nanorods were embedded in the hydrogen matrix clearly. Yeah, and both hydrogels have this microporous structure. Yeah, this structure will facilitate water transport within the hydrogen. We also characterize for FTR. As you can see, all the characteristics were observed, as well as using the UVs. Yeah, and you can see when we introduce black colored photothermal materials into the hydrogels can efficiently absorb the solar irradiation. Yeah, they usually show very broad solar absorption spectrum from 300 nanometer to 2500 nanometer. Yeah, and in contrast, this PVA pristine PVA samples, as you can see, almost have no solar irradiation. Yeah, above 400 nanometer. And then we use this homemade setup to test the solar vapor generation efficiency or the water evaporation rate of our hydrogel materials. And the results are summarized in this table. Yeah, as you can see, the PVA hydrogels with 1D nanorods show the highest SVD performance compared to all the semiconductor-based hydrogel systems. Yeah, they achieve about 2.8 kilograms square meter per hour, as well as with very high solar to vapor efficiency. And this performance is definitely better than the 3D nanoparticle one. Yeah. Oops. Okay, so in the next study, my student Stella synthesized 2D photothermal materials. Yeah. So we use the bulk crystalline polyethylene or bulk amorphous polyethylene as the raw materials, and through a normal cold bath assistant sonication technology, so we can successfully exfoliate these materials and obtain this crystalline polyethylene nanosheet or amorphous polyethylene nanosheet respectively. And then we wash these materials and disperse them in water and characterize them by ICM and as you can see, the crystalline polyethylene nanosheet is relatively smaller or have a higher aspect ratio. Yeah, the thickness is about 7 nanometers, while the diameter is about 300 nanometers. And in contrast, the amorphous polyethylene nanosheet have a thicker thickness that's about 20 to 30 nanometers, while the diameter is about 500 nanometers. So the crystalline polyethylene nanosheet have a higher aspect ratio. Yeah. We also test the photothermal materials of these materials. So under the same 10 minutes solar irradiation, so both of the materials achieve almost same photothermal performance. So achieving about 56 centigrade in 10 minutes. And then we use the same polyvinyl alcohol as a polymer matrix. Yeah, added very tiny amount. It can be trace amount, the 0.1% or 0.05% of 2D materials as a photothermal materials into the hydrogels. Yeah, and through the same cross-linking, freezing thaw process, so we successfully prepared the PVA hydrogels with 2D photothermal materials. Yeah, with different methods of the photothermal material. Yeah. Then we use the same setup to test the water evaporation rate of these materials. As you can see, the hydrogels loading only 1% of crystalline of crystalline polyethylene nanosheet show the best evaporation rate, yeah, achieving 4 kilograms per square meter per hour. Yeah, this result is very good, and we just submitted this study. Definitely, we compare this performance with all the PVA-based hydrogels. Yeah. As you can see, over 4.0 kilogram per square meter per hour is a really high evaporation rate, and this is resulting higher than all the other stuff systems. Yeah. So at the same time, our research also focus on the water management strategy, and my student Shudi conducted this work. Yeah. So in this study, we use graphene oxide because graphene oxide is relatively cheaper, and so that's why, and we can buy 1 gram of them. Yeah. So that's why I should use this 2-dimensional photosol materials instead of graphene nanochip. And we use graphene only 0.1 weight graphene oxide and photosol materials. And in her study, we use different polymer precursors, so including the PVA, polyvinyl alcohol, here or PEG as different polymer precursor to construct the hydrogen materials. And accordingly, we obtain these 3 composite hydrogen materials. Yeah. So we first characterize the morphology of these hydrogen materials, as you can see from the SM image. Yeah, all the hydrogens have micropore structure. However, interestingly, we find that this P here as a PPEG composite hydrogens, the pore size is relatively larger, and all the pores are interconnected, as you can see from this image. Yeah. So this structure is expected to show higher or fast water transport. So what's the reason? Yeah. So this result can be attributed to the difference of the glassy transition temperature between these raw materials. So specifically, the PVA does have a higher TG, yeah, that's about 50 centidegree. So therefore, and the frozen process that's conducted at minus 18 centidegree, the polymer chain, yeah, lack flexibility. So therefore, in the hydrogels, the growth of the water crystal was limited. So finally, we obtained a micropore structure with a lot of small pores. Yeah, that's the case of PVA hydrogels. However, in the case of P here or PPEG hydrogels, the TG of them is very low, so below minus 40 centidegree. So therefore, during the frozen process at minus 18 centidegree, the polymer chain still show high mobility. Yeah. So therefore, the crystalline, the water crystal in this hydrogen can grow larger and larger, not limited by the polymer chain. So therefore, finally, we will obtain very large pore size, yeah? And they are interconnected. And this structure, as I said, are expected to show high water transport, rapid transport, water transport, and finally, eventually, facilitate water evaporation. Yeah. So we definitely characterize these hydrogens or FTM or FTR or UVBs. Yeah. You can see all the characteristics of the different hydrogens were observed. Yeah, and all the hydrogens show a broad solar absorption spectrum. Yeah. So then we test the water evaporation performance of all these hydrogens as expected. Yeah, the PVA hydrogens, PEG hydrogens with graphene oxide as the photosol materials show highest water evaporation rate. Yeah, they achieve 3.6 kilogram per square meter per hour. Yeah, and this value is definitely higher than the PVA one. Yeah, PVA is about PVA here. That's about 2.8. Yeah. Kilogram per square meter per hour. Yeah, so it demonstrates that the rapid water transport definitely affect the SVG performance. Yeah, and this work conducted by 2022. So at that time, we found that 3.6, this value is the highest one compared to all the conventional and 2D hydrogen system. Yeah, but the last study we conducted in this year, and we break this record. Yeah. So definitely this hydrogen we will test the SVG performance of this hydrogen against the seawater. Yeah. So as you can see in the cycle test, these PEG hydrogens can display stable SVG performance even when you use seawater. The seawater was obtained from Harbor, Darling Harbor. Yeah, that's a real seawater from Sydney. Yeah, and all these materials they show very stable performance. Yeah, that's around 3.6 or 3.7 kilogram per square meter per hour. Yeah, we also use ISV mice to test the ion concentration of the collected water. Yeah, as you can see, all the distilled water show a very, very low salt concentration. Yeah, And this definitely made the drinking water standard by WHO. So this study here and the PEG, both of them show interconnected pores, yeah, and the pore size is very big. But what's the difference between them, resulting different evaporation performance? I read this question to Shudi, to my student, and then we realized that maybe the polymer structure can somehow further affect the SVD performance, not from the perspective of physics, but from the perspective of chemistry. Yeah? So that's why we think this topic may be interesting. So in this study, I asked Shudi to prepare a series of hydrogens. Yeah, we use the same 0.1 weight percent of graphite oxide as photochemical materials, all the same. Yeah, but we try different polymer precursors, as you can see, from the negative charge sulfuric acid group to the positive charge ammonia group with this kind of neutral ether group or hydroxy group. Yeah, use the same method we crossing them and frozen solve them to prepare hydrogens. Yeah. As you can see, all the hydrogens have the micropore structure, yeah? So, interestingly, is that we find that for this hydrogen, PN, yeah, this with the amine group as a pattern group, yeah, functional group, they show a higher intermediate water content. And these results are summarized in this figure. As you can see, PM hydrogens have a highest intermediate water content. And the intermediate water is believed to at a slightly excited state. So that means the evaporative enthalpy of intermediate water is lower than the free water. So that means if we have a higher intermediate water content, so in this case it's about 78%. 78% of the water inside the hydrogen intermediate water are active by the polymers, by the hydrogen itself. Yeah, so therefore under solidization, it can generate fast water evaporate. Yeah. So firstly, we use DIC to demonstrate this theory. So as you can see, through the DIC characterization, we definitely observe that the PEM show the highest equivalent water evaporation enthalpy. So we know that at room temperature, the water evaporation enthalpy is as high as 2,240 kilojoules per gram. Yeah. However, in our case, we reduce this number to about 1,000 kilojoules. Yeah. So we definitely tested the evaporation performance as expected. This hydrogen shows highest water evaporate because it had high content of intermediate water. Yeah. And then we definitely do this kind of second test against the seawater, and we definitely observe that the salt concentration is very low from the distilled water. Okay, like our last study, we developed a novel dual-layer hydrogen system. Yeah, on the top layer is composed of PVA and graphite oxide, and the bottom layer are made from this this polymer containing this positive charge ammonia group. We also added a certain amount of PVA because PVA can enhance the compatibility between these two layers. Yeah, because different hydrogens have different swelling ratio. Yeah, we don't want this two layers just a break. Yeah. So we characterize for FDR and UVVs, and first we demonstrate that the dual layer configuration definitely can enhance the heat insulation. So we test the temperature of the interface and the buffer water and observe a higher temperature difference compared to conventional homogeneous stream. Yeah, and we definitely test the evaporation performance. It's okay, 3.1 kilogram per square meter per hour. But more important, these hydrogens show a high salt rejection ability. So we test the SVD performance against seawater from the Sydney Bay, and also concentrated seawater. Yeah, as you can see, in this case, the obtained distilled water definitely have a very low salt concentration. Yeah, through the hydrogen system. Additionally, due to the introduction of this positive charge functional groups, our hydrogens also show good antimicrobial property. Yeah, remember that to achieve the same effect, we can kill 99.99% of the bacteria. To achieve the same effect, so conventional study usually introduce several nanoparticles or use the carbon quantum dots. Yeah, but both of them are expensive. We only need to tune the structure of the polymers and achieve this ability. Yeah. So finally, give a conclusion. So firstly, we investigate through our study. We found that the 2D materials, they have a high aspect ratio. So therefore, they have some advantage compared to 1D and 3D photothermal materials. Yeah. Because we only need 1/10 of the weight to save ultraviolet. Yeah. And secondly, the cryogens also display the desired properties, like the large pore size and interconnected parts. Thirdly, we also investigate this hydrophilic group hydrogens can be ranked in terms of this HVD performance and follow. So this amine group shows best HVD performance, but this ammonium group shows lowest HVD performance, and we demonstrate that the chemical structure of the hydrogen can also affect HVD performance, not just a physical property. Yeah. And finally, we developed this novel dual layer hydrogens and demonstrate that this dual layer have multi-function. Yeah, it can enhance the heat insulation, can kill the bacteria, can show very high salt rejection effect. Okay, finally, give thanks to my group members. This study conducted by Shudi, Cassie, and Stella, and also thanks my collaborator from UTS, and thanks ARC, ATSE, and New South Wales Government, UTS for their fund support, and also give thanks to my industrial collaborator. Finally, thanks Sean, thanks Michael, thanks all the organizing committee members to organize this fantastic conference, and thanks all the audience, and I'm happy to answer your questions.
Thank you. Interesting keynote presentation. We have time for one quick question. There we go. Yes.
Thank you for the great presentation. I'm not really familiar with much with material science, but I got a question on this hydrogel. I see there's recently been a lot of applications of hydrogel in wastewater treatment, trying to encapsulate or immobilize bacteria. How do you think your hydrogel material can also perhaps do that? And also, do you have any comments on this application? Is it feasible?
Yeah, as I mentioned, that the chemical structure of the hydrogen definitely determines a lot of things in different applications. In my application, I introduced this kind of positive charged groups, so therefore the hydrogen can kill the bacteria. Yeah, so within 1 hour of incubation, they can kill 99% or the 99%. Yeah, but if we change the chemical structure of this hydrogen, otherwise we use other materials, for example, PEG. Use the biocompatible materials, biodegradable materials, definitely can somehow increase the compatibility between the hydrogens and the microbiome or the tissue or the cells. Yeah. So I heard a lot of study about tissue engineering. They just use hydrogen material, yeah, to grow to grow the cells, the animal cells, yeah, on that and do the experiments. So again, the structure determines the property and for different applications. Yeah. Thank you.
All right, thank you. Well, we might now wrap up now.